Hey guys, welcome to video 86. Today we're going to take a look at the derivation of the equations for the endpoints of the AC load line. These equations are given in a lot of different textbooks and they're used routinely in analysis and design applications. But I've never seen anybody show explicitly where they come from. It's just like they're kind of pulled out of thin air. And I really don't like that. Wherever possible, I like to show, based on more or less first principles, where these things come from. And sometimes I can understand why it's not done because the derivations can be really long and hideous. But in this case, it's really pretty straightforward, and that's what we're going to take a look at today. Now, the circuit we're going to look at is just a typical Class A common emitter amplifier with voltage divider biasing. We could use a vacuum tube triode or pentode Class A amplifier as well, but this is what I'm going to go with. And over here we've got an AC load line with the Q point located in the center. It doesn't necessarily have to be there, but I figured, what the heck, let's just imagine it is centered, because that's what we're shooting for most of the time anyway. Let's start this discussion assuming from the outset that we have no idea what the equations are for the endpoints of the AC load line. So if we don't know those things, what do we know about the load line? Well, first of all, we know it has to intersect the Q point. And second of all, the slope is negative and it's equal to the reciprocal of the total resistance in the AC equivalent model. That would be R prime C plus R prime E. In this case, I fully bypassed the emitter, so R prime E is 0. And the slope of this line, M, is equal to negative 1 over R prime C. And in case you've forgotten, remember R prime C is equal to RC in parallel with RL. Now, what we've got to do next is go back and recall some basic algebra, and you may or may not remember that there are two standard equations for a line on the plane. One form is called the slope-intercept form, and it says that y equals mx plus b. Y is our dependent variable, x is our independent variable, m is the slope, and b is the y-intercept. Now, this form isn't going to be helpful to us because this b here, the y-intercept, is IC-SAT, and we don't know what that is yet. So we're not going to use this form. Instead, we're going to use what's called the point-slope form. Point-slope form. And this expression says y minus y sub 0, or y naught, is equal to m times x minus x naught. And in this form, we have the following identities. Of course, y is the independent variable, so I sub c equals y. Y sub 0, or y naught, is the y coordinate of the point we know, which is the Q point, so y naught is ICQ. M, of course, is the slope we've got here. X is our independent variable VCE, and x naught is VCEQ. It's the second coordinate of this known point. All right, so let me identify these and write them down, okay? So y is equal to I sub c, x is equal to VCE, m is the slope, of course, we already have that. All right, so y naught is equal to ICQ, and x naught is equal to VCEQ. Now, what we're going to do next is take all of these different identities we came up with and substitute them back into the original point-slope form equation, along with our identity for the slope. So that gives us I sub c minus ICQ equals the slope, negative 1 over R prime C, times VCE minus VCEQ. Okay, let's make a little room here and I'm going to carry this equation up to the top. And what we'll do next then is solve this for I sub c. And to do that, all we need to do is add ICQ to both sides. So that gives us I sub c equals ICQ minus 1 over r prime c times VCE minus VCE Q. What we'll do next is look at this equation and see what happens when we're in saturation. So in saturation, the Q point's moved all the way over here, and VCE equals 0, IC equals IC sat. All right, so we've got IC sat equals ICQ minus 1 over RC times 0 minus VCEQ. So because this is 0, we've got just negative 1 over RC times negative VCEQ. The negatives cancel. We get plus VCEQ divided by R prime C, and there's the equation that we've been using all along. What we're going to do next is see what happens in cutoff. All right, so let's start by solving this top equation for VCE, and that's going to give us VCE equals VCEQ plus R prime C times ICQ minus IC. And of course, in cutoff, IC equals 0. So we're going to just eliminate this term, and we get VCE cutoff equals VCEQ plus R prime C times ICQ. And there you go. Bob's your uncle. These are the derivations for the AC load line equations. Now, if we did have a non-zero resistance in the emitter, R prime E was something other than 0, all we'd have to do is add that on to this factor with R prime C. And I'll show you that on the next page, where I made a nice pretty version of all this stuff because I love you guys so much. And here it is. Okay, let's go on over to the next page and look at a circuit that I put together to show an example of all these calculations. I designed this circuit to get as close to a centered ACQ point as I could using standard resistor values, and all the analysis results are here. ICQ is 1.2 milliamps, VCEQ 5 volts. The rest of it, little RE, is based on assuming eta is 1.5 and V sub t is 26 millivolts for this transistor. Here's our AC equivalent collector resistance. Our AC equivalent emitter resistance is 0 because we fully bypassed the emitter, and the gain's pretty high at negative 130. Here's our IC sat and VCE cutoff calculations and the load line. Now, at this point, I want to give you guys a lab assignment, and what I'd like you to do is build the circuit, verify the voltage gain, and the DC measurements and so on here as well, and then verify that clipping occurs at Vout equals approximately plus or minus 5 volts, and that can only happen if this AC load line accurately describes the function of the circuit. And you can use just about any NPN transistor you want in here, say a 2N3904, 2N2222, and so on. All right, now what I want to do next is show you guys a couple of waveforms I generated using PSpice to analyze this circuit. On the left here, we've got the output voltage waveform with the input set for a 1 kilohertz sine wave with a peak amplitude of 80 millivolts. Now, this is more than enough to drive the amplifier into clipping, and we can see, of course, it's got the normal non-linearity that we'd expect, and it looks like we're clipping up here at around plus 5 volts on the positive output, negative 5 volts here on the negative swing, So that looks about like what we'd expect, but over here on the right I plotted the AC load line, and that is collector current versus the collector voltage minus the emitter voltage. That's VC minus VE, which is VCE. And we can see that the load line does pretty much line up with what we predicted. We're going to hit cutoff at about 10.2 volts. Saturation occurs at about 2.35 milliamps, so it really looks good. Now, it doesn't matter what waveform you use to drive the amplifier. Here I used a sine wave. You could use a triangle wave or whatever's convenient, but you just have to make sure that you drive the transistor into cutoff and saturation in order to get the entire load line shown here. Now, if we take a really close look at this load line, we'll see that it's not really a line at all, but rather it's an ellipse that's kind of squashed and stretched out here. And what's going on is the capacitors are not perfect short circuits at this frequency, so we're seeing a little bit of that effect coming into play here. If we were to lower the input frequency even further, then the ellipse would start to spread out and we'd see, much more of it being evident. But under normal circumstances for a well-designed amplifier, the AC load line should pretty much be a straight line like we've got here. And that concludes today's adventure in circuit analysis. And before we go, I'd just like to thank those of you that subscribe to my Patreon page. And I didn't even think about that until somebody on here suggested it. So thanks for that as well. And any help you guys can give along those lines is greatly appreciated. And I'll put a link to it in the description. And I'll see you guys next time around.